Welcome to Astro Odyssey. Explore the universe. Out in the vastness of our solar system, beyond the comfortable blue skies and gentle weather patterns of Earth, exist storms so enormous, so powerful, and so long-lived that they make the strongest hurricanes on our planet look like tiny whirlpools in a bathtub. These are storms bigger than Earth itself, cosmic tempests raging across alien worlds. Some lasting for centuries, others growing so massive they could swallow our entire planet whole. To understand these storms, we must first rethink what a storm actually is. On Earth, storms are powered by heat, moisture, and the rotation of the planet. Warm ocean water fuels hurricanes, rising air creates thunderclouds, and pressure differences drive winds across continents. But on the giant planets of our solar system, storms are driven by forces far more extreme. These planets are enormous balls of gas, with deep churning atmospheres that stretch thousands of kilometers downward. Instead of solid ground, there are layers upon layers of clouds made of ammonia, methane, water, and even exotic chemicals unknown on Earth. Deep within these atmospheres, heat rises from the planet's interiors, mixing with powerful jet streams that circle the planets at incredible speeds. The result is a perfect recipe for storms that dwarf anything we have ever experienced. The most famous of these storms is Jupiter's Great Red Spot, a swirling vortex that has been raging for at least 350 years. When early astronomers first pointed their telescopes at Jupiter in the 1600s, they noticed a strange red oval on its surface. They couldn't have known they were witnessing one of the largest storms in the solar system. Today, we know that the Great Red Spot is a gigantic, hurricane-like system, spinning counterclockwise in Jupiter's southern hemisphere. It is so large that Earth could fit inside it, with room to spare. Imagine a storm so big that our entire planet would disappear within its swirling clouds. But size is only part of what makes this storm incredible. The winds inside the Great Red Spot can reach speeds of over 400 kilometers per hour. It's faster than the most powerful hurricanes on Earth. And unlike Earth's storms, which usually fade after a few days or weeks, Jupiter's storm has persisted for centuries. To understand why, we need to look at the unique environment of Jupiter. Jupiter is a gas giant, composed mostly of hydrogen and helium. It has no solid surface, which means storms don't lose energy by making landfall the way hurricanes do on Earth, on our planet. When a hurricane moves over land, it quickly weakens because it loses access to the warm ocean water that fuels it. But on Jupiter, there is no land, just endless layers of atmosphere. That means storms can keep feeding on the planet's internal heat, growing larger and lasting far longer. Jupiter also rotates incredibly fast. A single day on Jupiter lasts only about 10 hours. This rapid rotation creates strong jet streams that slice across the planet's atmosphere, forming the colorful bands we see in images of Jupiter. Where these jet streams meet, turbulence builds, and storms are born. The Great Red Spot sits between two of these powerful jet streams, jack-like barriers that keep it trapped in place. Instead of drifting around the planet or breaking apart, the storm remains stable, spinning endlessly in the same region. Over time, smaller storms are pulled into it, merging with the larger vortex and feeding its strength. It's like a cosmic whirlpool, swallowing anything that comes too close. Spacecraft that have visited Jupiter, such as the Voyager probes in the 1970s and the Juno mission today, have given us detailed views of this enormous storm. They've shown that the Great Red Spot isn't just a surface feature. It extends deep into the planet's atmosphere, reaching depths of hundreds of kilometers. That means it's not just a cloud pattern. It's a massive, three-dimensional structure. But Jupiter doesn't just have one giant storm. Its entire atmosphere is filled with swirling vortices, some white, some brown, some red. Many of these storms are larger than Earth. Some form merge and disappear over time, while others persist for years or decades. In the early 2000s, astronomers watched as three smaller white storms merged into a single giant vortex, which later turned red, earning the nickname Red Spot Jr. It was like watching the birth of a new superstorm on a world far beyond our own. And Jupiter isn't the only planet with storms of this scale. Saturn, the ringed giant, also hosts enormous weather systems. Though Saturn appears calmer than Jupiter at first glance, it occasionally unleashes storms of unbelievable size. About once every few decades, a massive storm erupts in Saturn's atmosphere, wrapping around the entire planet like a white scar. These storms are called Great White Spots, and they can stretch for tens of thousands of kilometers. When the Cassini spacecraft was orbiting Saturn in 2010, it witnessed one of these storms in action. It began as a small bright spot, but over the course of weeks, it grew into a gigantic band encircling the planet. Lightning flashed within the storm, and powerful winds tore through the clouds. The energy released by this storm was enormous, far greater than any hurricane on Earth. What makes these storms possible is the immense size and energy of the gas giants. Jupiter and Saturn are not just bigger than Earth. They are dozens or even hundreds of times more massive. Their atmospheres are deeper, their winds faster, and their internal heat far stronger. This combination creates conditions where storms can grow to unimaginable sizes. On Earth, the largest hurricanes span about 1,000 kilometers across. But on Jupiter or Saturn, storms can reach tens of thousands of kilometers in diameter. That's the difference between a storm that covers a country and one that could swallow an entire planet. And yet, despite their size, these storms follow some of the same basic principles as weather on Earth. They are driven by heat, rotation, and the movement of aurora, in this case, gas. The same physics that creates a thunderstorm in the tropics also creates a planet-sized vortex on Jupiter. It's a reminder that the laws of nature are universal, shaping weather patterns on worlds both familiar and alien. As we continue exploring the solar system, we're discovering that storms bigger than Earth are not rare exceptions. They are a common feature of the giant planets, each one shaped by the unique conditions of its world. Some are made of ammonia clouds, others of methane, and some may even contain exotic chemicals that don't exist on Earth. These storms rage in environments with crushing pressures, freezing temperatures, or intense radiation. And yet, they follow the same fundamental rules of motion and energy that govern the weather outside your window. The idea of storms larger than our entire planet might sound like science fiction, but it's very real. Every time we look at Jupiter through a telescope, we're seeing one of these colossal storms in action. Every time a spacecraft sends back images of Saturn, Uranus, or Neptune, we're witnessing weather systems on a scale that defies imagination. These storms remind us that Earth is just one small world in a vast and varied solar system, where nature's forces can reach extremes far beyond anything we experience here. While Jupiter's Great Red Spot is the most famous giant storm in the solar system, it is far from the only one. If we turn our attention to Saturn, the beautiful ringed giant, we find a world that appears calm and pale from a distance, but hides some of the most dramatic weather events ever observed. Saturn's atmosphere is made mostly of hydrogen and helium, similar to Jupiter's. But its colors are softer, with golden and creamy tones instead of Jupiter's bold reds and browns. For a long time, astronomers believed Saturn's weather was less intense than Jupiter's, simply because its storms were harder to see. But that illusion was shattered when spacecraft began sending back close-up images. Beneath those smooth cloud layers, Saturn hosts storms so enormous that they can wrap all the way around the planet. These are not short-lived tempests, like hurricanes on Earth. They are planet-spanning outbreaks of energy, lightning, and turbulent clouds that can last for months and leave lasting scars in the atmosphere. One of the most fascinating types of storms on Saturn is known as the Great White Spot. These storms appear roughly once every 20 to 30 years, erupting suddenly and growing at incredible speed. At first, they look like small bright clouds in Saturn's upper atmosphere, but within days or weeks, they expand into gigantic systems that can stretch tens of thousands of kilometers. Eventually, they can encircle the entire planet, forming a massive white band that looks like a bright ring across Saturn's surface. Imagine a storm on Earth that starts over the Pacific Ocean and then grows until it stretches all the way around the equator, connecting back to itself. That is the scale of what happens on Saturn. The most detailed observations of one of these storms came from the Cassini spacecraft, which orbited Saturn from 2004 to 2017. In December 2010, Cassini detected the birth of a new great white spot. At first, it appeared as a bright cloud in Saturn's northern hemisphere. But within weeks, it expanded into a massive storm system. The clouds churned violently, forming swirling patterns and towering plumes that rose high into the atmosphere. As the storm grew, it began to wrap around the planet, forming a continuous band that stretched more than 300,000 kilometers in length. That is nearly the circumference of Earth multiplied several times. It was one of the largest storms ever observed in the solar system. Inside this storm, something even more dramatic was happening. Cassini's instruments detected powerful bursts of radio waves, which are signs of lightning. On Earth, lightning is common in thunderstorms. But on Saturn, these lightning bolts were far more powerful. Some of them released thousands of times. It's more energy than a typical lightning strike on Earth. The flashes were so strong that they lit up the surrounding clouds, creating brilliant bursts of light in the darkness of Saturn's atmosphere. Scientists believe these lightning storms were caused by massive convective currents, huge columns of warm gas, rising from deep within the planet. As the gas rose, it cooled and formed clouds, while turbulence built up electrical charges that eventually discharged as lightning. What makes Saturn's storms particularly interesting is their connection to the planet's seasons. Unlike Jupiter, which has almost no tilt, and therefore very little seasonal change, Saturn is tilted at about 27 degrees, similar to Earth's tilt of 23.5 degrees. This means Saturn experiences seasons, although they last much longer because the planet takes nearly 30 Earth years to orbit the Sun. Each season on Saturn lasts more than 7 Earth years. Scientists believe the great white spots are linked to these long seasonal cycles. As sunlight gradually warms one hemisphere, energy builds up in the atmosphere over many years. Eventually, this energy is released in the form of a massive storm, like a pressure valve suddenly opening after decades of buildup. But the great white spots are not the only impressive storms on Saturn. One of the most mysterious features of the planet is a giant hexagon-shaped storm at its north pole. Discovered by the Voyager spacecraft in the early 1980s, this strange structure looks like a six-sided jet stream circling the pole. Each side of the hexagon is longer than the diameter of Earth. The entire structure measures about 30,000 kilometers. What makes it even more fascinating is that it has remained stable for decades. When Cassini arrived at Saturn more than 20 years after Voyager's discovery, the hexagon was still there, spinning quietly around the pole. The hexagon is not just a visual curiosity. It is a powerful storm system with winds reaching hundreds of kilometers per hour. At its center lies a massive hurricane-like vortex similar to a giant cyclone at the pole. But unlike hurricanes on Earth, which drift across oceans and continents, Saturn's polar storm remains locked in place. The hexagon itself is thought to be caused by a jet stream moving at different speeds at different latitudes. Laboratory experiments on Earth have even recreated similar hexagonal patterns in rotating fluids. suggesting that the shape is a natural result of the physics of rotating atmospheres. Despite their size and power, Saturn's storms are often hidden beneath its hazy cloud layers. The planet's upper atmosphere contains a thick layer of ammonia ice clouds, which can obscure the more dramatic weather happening below. This is why Saturn appears calmer than Jupiter when viewed through a telescope. But when spacecraft like Cassini use instruments that can see deeper into the atmosphere, they reveal a world of swirling storms, lightning, and turbulent winds. Another remarkable aspect of Saturn's storms is their speed. Winds in Saturn's atmosphere can reach up to 1,800 kilometers per hour near the equator. That is more than 4 times the speed of the strongest hurricanes on Earth. These powerful winds stretch across the planet in long bands, similar to those on Jupiter. Where these bands meet, storms can form and grow, sometimes merging into larger systems. Over time, these interactions create the massive storms that define Saturn's weather. The energy driving these storms comes from deep within the planet. Like Jupiter, Saturn radiates more heat into space than it receives from the Sun. This internal heat rises through the atmosphere, creating convection currents, giant columns of rising and falling gas. These currents are the engines that power Saturn's storms. Combined with the planet's rapid rotation, Saturn completes a full spin in just over 10 hours. They create a dynamic and ever-changing atmosphere. If you could somehow float above Saturn's clouds, you would witness a world of constant motion. Vast storm systems would stretch across the horizon. Lightning would flash in the distance, and powerful winds would sweep clouds into swirling patterns. It would be a place of incredible beauty and terrifying power. But of course, no human could survive such an environment. The pressures and temperatures deep in Saturn's atmosphere would crush and vaporize anything from Earth. Saturn's storms remind us that the solar system is far more dynamic than it might seem from afar. Even a planet that appears calm and peaceful can hide storms larger than our entire world. These massive weather systems are not just curiosities. They are clues to how giant planets work. By studying Saturn's storms, scientists learn more about atmospheric physics, its planetary formation, and the behavior of fluids under extreme conditions. And Saturn is only one of the gas giants. Beyond its rings lie even more distant worlds, Uranus and Neptune, where storms rage in the darkness of the outer solar system. On those icy giants, winds can blow faster than the speed of sound and dark. Mysterious vortices appear and disappear like cosmic hurricanes. Compared to those distant tempests, even Saturn's planet-spanning storms are just part of a much larger story, one that stretches across the entire solar system and beyond. Far beyond the orbit of Saturn, where sunlight is faint and the temperatures plunge to extremes, lie the icy giants Uranus and Neptune. These distant worlds are very different from Jupiter and Saturn. Instead of being made mostly of hydrogen and helium, Uranus and Neptune contain larger amounts of water, ammonia, and methane deep within their interiors. This gives them their nickname, ice giants. From Earth, they appear as cold, bluish spheres drifting in the darkness of the outer solar system. For many years, scientists assumed that these planets would be relatively calm because they receive so little heat from the sun. But when spacecraft finally visited them, they discovered something surprising. Despite their frigid temperatures and distant location, Uranus and Neptune host some of the most violent storms in the solar system. Storms that can grow large enough to rival or exceed the size of Earth itself. The first close look at these distant worlds came from NASA's Voyager spacecraft, which flew past Uranus in 1986 and Neptune in 1989. When Voyager 2 approached Uranus, scientists were puzzled. The planet appeared almost featureless, like a smooth blue-green ball. There were no obvious storms, no swirling bands, and no giant red spots like those on Jupiter. Uranus looked calm and quiet, almost boring compared to its more dramatic neighbors. But this appearance was deceptive. Uranus is tilted on its side, with an axial tilt of about 98 degrees. That means it essentially rolls around the sun like a ball, with one pole facing the sun for decades at a time, while the other remains in darkness. This extreme tilt creates unusual seasonal patterns that last for decades. At the time of Voyager's flyby, one hemisphere of Uranus had been facing the sun for years, and the atmosphere appeared relatively stable. As time passed and astronomers continued to observe Uranus with more advanced telescopes, they began to notice changes. Bright storm clouds started appearing in its atmosphere. Some of these storms were enormous, stretching thousands of kilometers across. Unlike the colorful storms of Jupiter and Saturn, the storms on Uranus often appeared as bright white or pale features against the planet's blue-green background. These storms were caused by rising clouds of methane ice, formed when warmer gases from deeper in the atmosphere rose upward and cooled, although Uranus may look calm at times. It is capable of producing storms that grow rapidly and then fade away, only to be replaced by new ones. But if Uranus was surprising, Neptune was truly shocking. When Voyager 2 approached Neptune in 1989, scientists expected a quiet, frozen world. After all, Neptune is the most distant planet from the Sun, receiving only a tiny fraction of the sunlight that warms Earth. Temperatures in its upper atmosphere can drop to around minus 200 degrees Celsius. But instead of a calm planet, Voyager found a world filled with powerful storms and incredibly fast winds. In fact, Neptune has the fastest winds ever measured in the solar system. Some of these winds reach speeds of over 2,000 kilometers per hour, faster than the speed of sound on Earth. One of the most famous features discovered on Neptune was the Great Dark Spot. This storm was similar in appearance to Jupiter's Great Red Spot, but instead of being red, it was a deep, dark blue or black. The Great Dark Spot was an enormous vortex, about the size of Earth, spinning through Neptune's atmosphere. Around it were bright white clouds, formed by methane ice crystals. These clouds were likely created by air being forced upward around the edges of the storm, much like the towering thunderheads that form around hurricanes on Earth. The Great Dark Spot was a powerful and dynamic storm. Unlike Jupiter's Great Red Spot, which has lasted for centuries, Neptune's dark storms appear to be much more temporary. When the Hubble Space Telescope observed Neptune a few years after Voyager's flyby, the original Great Dark Spot had disappeared. It was gone, as if it had never existed. But in its place, new dark spots began to appear in different parts of the planet. These storms seemed to form, drift across the atmosphere, and then fade away over the course of a few years. This behavior makes Neptune's storms some of the most mysterious in the solar system. Scientists are still trying to understand exactly how they form and why they disappear. One theory is that the storms are giant vortices, similar to hurricanes. They're created by the interaction of fast-moving jet streams in the planet's atmosphere. Over time, these vortices may become unstable and break apart, causing the storms to fade away. Another possibility is that changes in temperature or atmospheric composition cause the storms to lose energy and dissipate. What makes Neptune's storms especially remarkable is the environment in which they exist. Despite being so far from the sun, Neptune actually emits more heat than it receives. Deep within the planet, residual heat from its formation continues to escape into space. This internal heat helps drive convection currents in the atmosphere, creating powerful winds and storms. Combined with the planet's rapid rotation, it completes a full spin in about 16 hours. This internal heat creates a highly dynamic atmosphere. If you could somehow observe Neptune's storms up close, you would see dark, swirling vortices surrounded by bright icy clouds. The winds would howl at speeds far beyond anything on Earth. The temperatures would be unimaginably cold, and the sky would have a deep blue hue from the methane in the atmosphere. It would be a strange and alien world, where storms the size of planets form and vanish like shifting shadows. Even more intriguing is the fact that Neptune's storms may be linked to seasonal changes, just like those on Saturn and Uranus. But because Neptune takes 165 Earth years to orbit the Sun, each season lasts for more than 4 decades. That means the storms we see today may be part of long-term atmospheric cycles that we are only beginning to understand. The discovery of these storms on Uranus and Neptune changed our understanding of the outer solar system. It showed that even in the coldest, darkest regions, planets can have dynamic and powerful weather systems. The energy driving these storms doesn't come mainly from the Sun, but from deep within the planets themselves. This means that storms bigger than Earth are not limited to the warm, bright regions of the solar system. They can exist even in the frozen darkness billions of kilometers away. And these icy giants may not be unique. As astronomers discover more planets, orbiting other stars, they are finding worlds similar in size and composition to Uranus and Neptune. Some of these exoplanets are much closer to their stars, meaning their atmospheres are heated to extreme temperatures. On such worlds, storms could grow even larger and more violent than anything in our solar system. In fact, some exoplanets may have storms that cover entire hemispheres with winds blowing at thousands of kilometers per hour. The storms of Uranus and Neptune are a reminder that the solar system is full of surprises. Even the coldest planets can host violent weather, and even the most distant worlds can produce storms larger than Earth. As we continue to explore the outer planets and discover new worlds beyond our solar system, we may find storms even more massive and more powerful than anything we've seen so far. These distant tempests are not just scientific curiosities. They are windows into the complex and dynamic processes that shape planets across the universe. Beyond the familiar planets of our solar system lies an even more extreme realm where storms larger than Earth may be not just possible. These are the worlds known as planets, orbiting stars beyond our Sun. Since the first confirmed discovery of an exoplanet in the 1990s, astronomers have identified thousands of these distant worlds, and many of them are unlike anything we see in our own planetary neighborhood. Some orbit extremely close to their stars, others are locked in perpetual darkness, and many experience temperatures and pressures so extreme that the very concept of weather takes on an entirely new meaning. On these alien worlds, storms can grow to planetary scales, driven by intense heat, violent winds, and exotic atmospheric chemistry. One of the most dramatic types of exoplanets is known as the hot Jupiter. These are gas giants similar in size to Jupiter, but they orbit incredibly close to their parent stars, sometimes closer than Mercury is to the Sun. As a result, their atmospheres are heated to thousands of degrees Celsius. On some hot Jupiters, the temperature difference between the day side and the night side can be extreme. One side of the planet permanently faces the star, baking under relentless radiation, while the other side remains in perpetual night. This temperature contrast creates powerful winds, as hot gas rushes from the day side to the night side, trying to redistribute heat. These winds can reach speeds of several kilometers per second. It's far faster than any winds found in our solar system. In such environments, storms are not gentle systems of clouds and rain. Instead, they are massive atmospheric engines, spanning huge portions of the planet. Some hot Jupiters may have storms that stretch across entire hemispheres, with swirling clouds of vaporized metals and molten rock. On these worlds, it can literally rain iron or glass. Observations of certain exoplanets suggest that silicate particles, essentially tiny grains of glass, form in the atmosphere and are carried by extreme winds. When these particles fall, They don't drift gently downward like snowflakes. They are blasted sideways at incredible speeds, creating horizontal storms of razor-sharp glass. In such conditions, a single storm system could easily be larger than Earth itself. Astronomers cannot yet see these storms directly in detail, but they can detect their presence through changes in light. When an exoplanet passes in front of its star, a small fraction of the starlight filters through the planet's atmosphere before reaching Earth. By analyzing this light, scientists can identify the chemical composition of the atmosphere and detect temperature differences between regions of the planet. These measurements have revealed evidence of strong winds, extreme heat redistribution, and massive storm systems. In some cases, the hottest point on a planet is not directly beneath the star, but shifted eastward by powerful winds, clear evidence of planet-wide atmospheric circulation. Another class of exoplanets known as ultra-hot Jupiters takes these extremes even further. On these worlds, temperatures can exceed 3,000 degrees Celsius, hot enough to break apart molecules and strip electrons from atoms. The atmosphere becomes a glowing, electrically charged gas. In such conditions, storms may behave more like plasma flows than traditional weather systems. Magnetic fields could interact with the charged atmosphere, creating enormous electromagnetic storms unlike anything seen on Earth. These storms could cover vast regions of the planet, driven by both thermal energy and magnetic forces, creating a type of weather that blurs the line between atmospheric science and astrophysics. But it's not only gas giants that host extreme storms. Some rocky exoplanets, especially those classified as super-Earths, may also experience storms on unimaginable scales. Super-Earths are rocky planets larger than Earth, but smaller than Neptune. Many of them orbit close to their stars, leading to extreme surface conditions. On some of these worlds, the surface may be partially molten, forming oceans of lava instead of water. Above these lava seas, thick atmospheres filled with vaporized rock could form. Winds would carry this vapor around the planet, where it might cool and condense, raining molten material back onto the surface. The result would be a global cycle of rock evaporation and condensation, a kind of weather system made entirely of stone. In such an environment, storms could engulf entire continents, or even the whole planet. Instead of clouds made of water droplets, the sky would be filled with clouds of mineral vapor. Lightning might still occur, generated by electrical charges and turbulent clouds, but it would flash through skies, glowing from intense heat. These storms could last for years or decades, constantly reshaping the planet's surface. Compared to these alien tempests, even the largest storms on Jupiter or Saturn might seem modest. One of the most fascinating possibilities involves planets that orbit red dwarf stars. Red dwarfs are smaller and cooler than our sun, but they are also far more active. They frequently produce powerful stellar flares that blast nearby planets with radiation. Many exoplanets discovered so far orbit very close to these stars, often becoming tidally locked, with one side permanently facing the star. On such planets, storms may form along the boundary between day and night, where extreme temperature differences create powerful atmospheric circulation. These storms could form a permanent ring around the planet, stretching for tens of thousands of kilometers. In some cases, the storm systems could be larger than Earth and persist for incredibly long periods, reshaping the planet's climate entirely. Computer simulations suggest that, on some exoplanets, storms could dominate the entire atmosphere. Instead of multiple separate weather systems, there might be just one or two gigantic storms that control global circulation. These storms could act like planetary scale engines, transporting heat, chemicals, and energy around the world. They might even influence the planet's evolution over time, affecting how heat escapes into space and how the atmosphere changes. What makes the study of exoplanet storms so exciting is that it pushes our understanding of physics to its limits. The same basic laws, gravity, fluid dynamics, thermodynamics, apply everywhere in the universe. But when those laws operate under extreme conditions, they produce results that seem almost unbelievable. Storms bigger than Earth are not violations of nature's rules. They are natural outcomes when those rules are applied on a massive scale. With immense energy and time, these discoveries also force us to rethink what is considered normal weather. On Earth, we measure storms in kilometers and days. On exoplanets, storms may be measured in planetary diameters and decades. A single storm could be a defining feature of an entire world, shaping its climate, chemistry, and even its appearance from space. Some exoplanets may always look stormy, with constantly shifting cloud patterns that never settle into calm conditions as telescopes become more powerful. Scientists hope to directly observe weather patterns on exoplanets in greater detail. Future space telescopes will be able to map temperature differences across distant worlds and track changes over time. This could allow astronomers to watch storms form, evolve, and dissipate on planets dozens or hundreds of light years away. When that happens, we may discover storms even larger and more powerful than anything we can currently imagine in the grand picture of the universe. Earth's storms are relatively gentle and fleeting. They are shaped by oceans, continents, and a thin atmosphere. But on other worlds where atmospheres are deeper, gravity is stronger, energy flows are more intense, storms can grow to truly planetary scales. These alien tempests remind us that Earth is just one example of how a planet can behave. Across the galaxy, storms bigger than Earth may rage endlessly. Unseen by human eyes, but following the same fundamental laws that govern the winds and clouds above our own world. As we continue to explore the solar system and discover new worlds beyond it, storms bigger than Earth are no longer just distant curiosities. They are becoming key pieces of a much larger puzzle, one that helps us understand how planets form, evolve, and behave over billions of years. These massive storms are not simply chaotic weather systems. They are part of the deep engines that drive planetary atmospheres. By studying them, scientists gain insight into the physics of fluids, the transfer of heat, and the dynamics of rotating worlds. Every giant vortex on Jupiter, every planet-wide storm on Saturn, and every dark spot on Neptune carries clues about the hidden interiors of these planets and the forces shaping them. Take Jupiter's Great Red Spot, for example. For centuries, it has served as a natural laboratory for studying storms. By observing how it changes over time, how it shrinks, stretches, interacts with surrounding jet stream, scientists learn more about the behavior of fluids under extreme conditions. The storm's persistence also tells us about Jupiter's internal heat and atmospheric structure. Without a solid surface to disrupt it, the storm can continue feeding on energy from below. This helps researchers understand not just Jupiter, but also other gas giants across the universe. If similar conditions exist on exoplanets, then massive long-lived storms may be a common feature of giant worlds. Saturn's storms, with their powerful lightning and planet-encircling cloud bands, reveal another important piece of the puzzle: the role of seasons and internal heat. The great white spots appear only once every few decades, suggesting that the planet's atmosphere slowly builds up energy before releasing it in a dramatic outburst. This teaches scientists about long-term atmospheric cycles, patterns that unfold over years, decades, or even centuries. Understanding these cycles helps researchers interpret data from exoplanets, where storms might last far longer than any human lifetime. When we see changes in the brightness or temperature of a distant world, those changes may be linked to storms similar to those on Saturn. The storms of Uranus and Neptune provide yet another perspective. These icy giants show that even in the cold, dark reaches of the solar system, powerful storms can exist. Their winds, some of the fastest ever recorded, are driven not by sunlight, but by heat escaping from deep within the planets. This discovery changed the way scientists think about planetary weather. It showed that the sun is not always the primary source of atmospheric energy. Instead, internal heat can play a major role, especially on large planets. This idea is crucial when studying exoplanets, many of which orbit far from their stars or receive very little sunlight. As technology advances, our ability to observe these distant storms is improving. Space telescopes like the James Webb Space Telescope are already giving us more detailed views of exoplanet atmospheres. By analyzing the light passing through these atmospheres, scientists can detect temperature differences, cloud patterns, and chemical signatures that hint at massive storms. In the future, even more powerful telescopes will allow us to map these weather systems in greater detail. We may be able to watch storms form and evolve on planets dozens of light years away. Much like meteorologists track hurricanes on Earth today, future missions to the outer planets will also deepen our understanding of giant storms. Probes sent into the atmospheres of Jupiter, Saturn, or even Uranus and Neptune could measure wind speeds, temperatures, and chemical compositions directly. These missions would provide valuable data about how storms form, how deep they extend, and how long they can last. Imagine a spacecraft diving into the swirling clouds of Jupiter's Great Red Spot, sending back real-time measurements from inside a storm bigger than Earth. Such a mission would transform our understanding of planetary weather. But beyond the science, there is something deeply inspiring about these enormous storms. They remind us of the sheer scale and power of the universe. On Earth, we measure storms in kilometers and hours. A powerful hurricane might cover a region the size of a small country and last for a week or two. But on other worlds, storms can span entire planets and endure for centuries. These storms challenge our imagination and force us to think beyond the familiar. They show us that nature's forces are not limited to the scale of our own world. They also highlight the delicate balance that makes Earth so special. Our planet has storms, but they are relatively small and short-lived compared to those on the gas giants. Earth's solid surface, moderate atmosphere, and balanced energy inputs keep its weather systems in check. Hurricanes eventually make landfall and lose strength. Thunderstorms dissipate after a few hours. Even the most powerful storms on Earth are temporary. This balance allows life to thrive. If Earth had an atmosphere as deep as Jupiter's, or winds as fast as Neptune's, the environment would be far more hostile. The study of giant storms also has practical benefits. The same physics that governs a massive vortex on Jupiter also applies to weather systems on Earth. By studying how these storms form, interact, and persist, scientists can improve their understanding of fluid dynamics and atmospheric behavior. This knowledge can help improve weather forecasting, climate models, and even the design of aircraft and spacecraft. In this way, studying storms millions or billions of kilometers away can have real-world applications here at home. Looking further into the future as humanity begins to explore the outer solar system, and perhaps even travel to other stars, understanding planetary weather will become increasingly important. Any mission to the gas giants will need to account for powerful winds, lightning, and turbulence. Future explorers may one day orbit or even descend into the atmospheres of these worlds. Knowing where storms are likely to form, how they behave, and how long they last could be critical for the safety and success of such missions. Even more intriguing is the possibility that some exoplanets with massive storms might still be habitable in certain regions. On tidally locked planets, for example, the boundary between the hot day side and the cold night side might host permanent storm systems. These storms could redistribute heat, creating zones where temperatures are more moderate. In such regions, conditions might be suitable for life. Studying these storm systems could help scientists identify which exoplanets are most likely to support life, guiding future searches for habitable worlds. In the end, storms bigger than Earth are more than just dramatic features of distant planets. They are windows into the complex processes that shape worlds across the universe. They teach us about the power of heat, rotation, and atmospheric motion. They reveal the diversity of planetary environments, from the scorching atmospheres of hot Jupiters to the icy winds of Neptune, and they remind us that Earth, with its gentle rains and manageable storms, is a rare and precious place. As our technology improves and our exploration continues, we will undoubtedly discover even more extreme storms, perhaps ones that make Jupiter's great red spot seem small by comparison. Somewhere out there, storms may rage across entire hemispheres or swirl endlessly around planets we have yet to detect. Each new discovery will expand our understanding of the universe and our place within it. And every time we look up at the night sky, we can remember that beyond the calm stars, there are worlds where storms larger than our entire planet are raging in the darkness. Following the same universal laws that govern the winds and clouds of Earth,